In this video, we will see that if there is an already existing binary search tree, how we can insert another element into it, followed by the deletion of any element from the binary search tree and the related time complexities. So in the previous class, we saw that how we can create a binary search tree, and the in-order traversal of a binary search tree will always produce a sorted list of elements in the ascending order. Okay. So now let's see what about its insertion and deletion. We created a binary search tree. We can follow the same procedure for insertion and deletion. So let's take a quick look into it. So I have already created the binary search tree that we had already created in the previous lecture. So let's say now that we want to insert an element, say the element is 40. So what do? We first go to the root node, we check. So now the key that I want to insert is less than the root value. So we go to the left subtree. If the key to be searched would have been greater than the root value, then we would have went to further search in the right subtree. Okay, because this is exactly how we created the binary search tree. So for insertion also, whenever we are now going to search for insertion, be it for deletion, we are going to search in the same pattern. Okay, so we searched here. So 40 is less than 45. So now see what is happening here. Your search space gets divided into two and basically discarding the right subtree's search space. So now your search space is only to the left of 45. Okay, so it's only from here. You are not going to search for 40 in the right subtree. So my search space has reduced to half, which is only the left subtree. So in the next step, now we will reach to the root node of the left subtree. Okay, so it is 39. Now what happens? See, your key is 40 and the value of the root is 39. So here 40 is greater than 39. So we know that if we want to insert 40, we have to go to the right of 39. So we go to the right of 39. What do we find? That it has no right child as of now. So we can directly insert the node 40 here. Okay. Now let's say the next element that I want to insert is, okay, I want to next insert element 62. Okay. So for that, now what will happen is, the process is similar to what we have done just now, that is during the insertion of the element 40. So first we go here to the root of the tree and we check. Now 62 is greater than the root value. So instead of going to the left subtree, we are now only going to search in the right subtree for an ideal place to insert 62. So again in this, now my search space has been reduced by half. So I am not going to search the left subtree anymore. I will just search the right subtree, which is this. Okay. So after 45, we understood that we definitely have to go to the right subtree. So we go to the next root. This is 56. And the key that I want to insert is 62. So now 62 is greater than 56. So we go to the right of 56. As we go to the right of 56, next root node that we encounter is 78. Now the key that we want to insert 62 is less than 78. Okay, so here also what happens, we go now our search space here also gets divided by 2. It's divided by 2, definitely it gets reduced by half. So since 62 is less than 78, therefore we go to the left of 78. So as we do that, we reach to the next node, which is 67. Now the key that I want to insert is less than 67. So I again go to the left of 67 and I find that there is no node to the left of 67. So now I can directly insert 62. So what we have observed till now is, say, let's start from 45 and we want to insert 62. So as soon as we come to 45, we reduce our search space by half by eliminating the search space of the left subtree, and now we are only searching in the right subtree. Again, as we come to the node 56, here also we find that 62 is greater than 56. So again we have reduced our search space by half, that is, we are not going to search the left subtree of 56. Instead, our search space is only the right subtree of 56. Now as we come down to the node 78, what happens, that now your key is less than 78. So we eliminate the right subtree of 78 from our search space. Instead, we are now only going to search for an ideal place at the left subtree of 78. So again there is a reduction in our search space by half. So we can see that every time the comparison loop is running, we are going to the next node, our search space gets reduced by half. And when this happens, what will be the time complexity to search for an ideal place to insert any key element? So you have to understand that every time you are going to the next node for searching the ideal place for comparison, our search space is getting reduced by half. Okay, so when such things happen, this you can find out this pattern. Okay, this is a pattern. So whenever you will see that this happens, we can say that the time complexity of such a task is big O of log n, and since it is getting reduced by half, so it's 2 at the base. Okay, so searching for so if you say what is insertion of an element, what steps are we following for insertion of an element in a binary search tree? So what we are doing, we are basically, first we are searching for an ideal place. Okay, and then what we are doing, we are basically inserting it, that is updating a few links. Guess how are we going to update that? Like when we inserted 40, what did we do? We updated the link of 39's right child, which was null initially. We updated it to 40. Correct? We updated it so that the right child of node 39 now points to this. Similarly, when we found the correct place for 62, which is here, we updated the links, we updated the pointer values so that the left child of node 67 now points to the newly created node 62. Initially, this pointer was null, but now since we want to insert 62, we are going to update it from null to point the new node, which is 62. So basically, if you say here, for insertion of any element into a binary search tree, we are basically doing two things. Firstly, we are searching for an ideal place to insert the element, and once we find the ideal place, we are simply updating the links, or you can call it as the pointers. Okay. So searching is taking time, log n. We saw y. I guess you all have understood here why. And then updation will take big O of 1. So which is greater? Log n. So we can say that to insert an element or the insertion of any element into an already existing binary search tree will take time of big O of log n. Okay, but the problem here is that this is the best and average case, this is the best and average case time complexity. Okay, now let's take up another example of a binary search tree. Say these are the elements in my binary search tree. Now what will happen? Say I ask you to insert element 97. What will happen here? We'll first go to the root node. We see that 97 is greater than 45. So we are going to the next node. So again 97 is greater than 65. So we go to the next one. 97 is again greater than 80. So we go to the right child of 80 again. 95, which is again less than the key that we want to insert. So we go to its right child. It was already null. So we can insert 97 here. How many? Now my question here is, how many nodes did you have to search to find the ideal place for 97? I think you all will agree here that we had to search all the nodes of a binary search tree. So if we can now say this, if a binary search tree contains n nodes and the tree is skewed. So the tree we saw right now, this one, is an example of a skewed binary tree. So in case of a skewed binary tree, insertion will take big O of n time, because you can see that to insert an element into a right skewed tree, we had to traverse all the nodes present in the binary search tree. So for insertion into a binary search tree, the best and the average case time complexities are big O of log n, but the worst case time complexity is big O of n. And which is the worst case? That the binary search tree itself is a skewed one, either right or left, but it is a skewed tree. In that case, we will have to traverse all the n nodes before we find the ideal place to insert our element. Okay. Now you can understand from this that for deletion also same thing will happen. Okay, what will happen in case of deletion? I'll just show it here itself and I'll not take much time. Say I ask you to delete the element 32. So what will happen? Just show you quickly. I'll delete all these marks. Okay, so now I want to delete the element 32. So how we are going to proceed for this? We are going to check the root node value 45. Now the value that you are searching for is less than 45. So you go to its left subtree. So we are again eliminating the right subtree and our search space is getting reduced by half. As we go to 39, we find out that the element we are searching for, which is 32, is less than 39. So we go to the left child of 39. We come to 12. Now 32 is greater than 12. So we go to the right of 12. To the right of 12 we have 34. 32 is less than 34. Therefore we go to the left of 34. As soon as we find this element, we can delete it. So deletion will, as you reach here, you will just have to again update a few pointers and free this memory. That's it. Okay. Now I hope it's very clear how deletion will take place. So basically in deletion what will happen, here we were searching for an ideal place, same thing will happen. You are going to search for the element that you want to delete, and after you find it, you are going to update the links. So searching again, because we are searching in the same type of tree, that is the binary search tree. So searching will again take time, big O of log n for deletion also, and updating the links will take time, big O of 1. So for deletion also the time complexities remain same. Okay. And in the case of a skewed binary search tree also what will happen, for deletion will take time, big O of n. Why? Because our first step is searching the element, searching where the element is located. So when that happens, searching will take n time. Okay, because all the nodes have to be traversed to reach at the correct position. As soon as you will reach, say I want to delete, I'll just show you an example quickly. Say I want to delete 95. So we are going to first come here. 95 is given to 45, we go here, then again go to its right child. As soon as we encounter 95, we are going to update. So this link should now point to this. Correct? So the time complexities remain same for insertion and deletion in case of a binary search tree. I hope binary search tree topic is now clear to you all. Thank you.